In the realm of cosmic explosions, the universe showcases some of the most extreme and awe-inspiring phenomena, each dramatically shaping the evolution of galaxies, stars, and the very fabric of space itself. Having introduced the categories of supernovae, quasars, and gamma-ray bursts, it's important to examine each in greater detail to fully appreciate the raw power and significance of these cosmic events. Let's start with supernovae, the titans of stellar death. When a large star, many times the mass of our Sun, reaches the end of its life cycle, it can no longer sustain the nuclear fusion reactions that counterbalance gravity's inward pull. In some cases, the core collapses suddenly, creating a violent explosion that outshines entire galaxies for a brief period. These explosions release an incredible amount of energy, on the order of 1044 joules, in just a matter of seconds. To put that into perspective, this is roughly equivalent to the energy output of the Sun over its entire 10 billion-year lifetime, but unleashed in just moments. There are two primary types of supernovae: Type Ia and core collapse supernovae. Type Ia supernovae occur in binary systems where a white dwarf star accretes matter from its companion until it reaches a critical mass and undergoes a thermonuclear runaway, exploding completely. These explosions are especially important because they serve as standard candles for measuring vast cosmic distances due to their consistent intrinsic brightness. Core collapse supernovae happen when massive stars, typically at least 8 times the Sun's mass, deplete their nuclear fuel, causing their core to collapse under gravity and trigger an explosion. The remnants of these supernovae often form neutron stars or black holes, compact objects with densities and gravitational fields far beyond what we experience on Earth. One famous example of a supernova is SN 1987A, which exploded in the Large Magellanic Cloud, a nearby dwarf galaxy visible from the southern hemisphere. Detected in 1987, SN 1987A provided astronomers with a wealth of information about the processes following a stellar explosion, including the formation of new elements and the propagation of shock waves through space. By studying the light curves and nucleosynthesis products of this supernova, scientists gained crucial insights into how heavy elements like iron and nickel are produced and distributed, ultimately contributing to the elemental diversity necessary for planets and life to exist. Moving beyond the explosive deaths of stars, quasars represent a different kind of cosmic powerhouse involving supermassive black holes, which reside at the centers of many galaxies, including our own Milky Way. A quasar, short for quasi-stellar radio source, is the intensely bright, energetic region surrounding an actively feeding supermassive black hole. When vast amounts of matter fall into this black hole's accretion disk, gravitational forces compress and heat the gas to extremely high temperatures, causing it to emit enormous quantities of electromagnetic radiation across the spectrum: visible light, X-rays, radio waves, and more. The energy output of quasars can outshine their entire host galaxies many times over, sometimes releasing energy equivalent to the light of 1,000 galaxies combined. This extraordinary luminosity is powered by the black hole accreting mass at rates far greater than the steady feed of typical galactic nuclei. The radiation pressure from this process can drive powerful jets and winds, impacting the surrounding galactic environment by regulating star formation and redistributing gas. Quasars were most abundant in the early universe, peaking roughly between 10 and 12 billion years ago, highlighting their role in the growth of galaxies and the assembly of large-scale cosmic structures. The discovery of quasars in the 1960s challenged previous notions about galaxy centers, indicating that black holes influence far more than just their immediate surroundings. One particularly luminous quasar, known as 3C273, was the first to be confirmed at a cosmological distance and remains a benchmark for understanding these objects. By studying quasars, astronomers gain clues about the early stages of galaxy formation and the physics of extreme gravity and magnetism. Finally, at the very edge of known cosmic violence, gamma-ray bursts, GRBs, stand as the most intense explosions observed in the universe since the Big Bang. GRBs emit brief but extraordinarily bright flashes of gamma-ray photons, the highest energy form of electromagnetic radiation. These bursts can release, in just seconds, as much energy as the sun will emit over its entire 10 billion-year life, making them the brightest events ever detected at gamma-ray wavelengths. There are two main classes of GRBs: long-duration bursts lasting more than 2 seconds, and short-duration bursts lasting less. Long GRBs are generally associated with the collapse of extremely massive stars, much larger than those involved in typical supernovae, leading to the formation of black holes and producing narrow, relativistic jets that beam intense gamma rays toward Earth. Short GRBs are thought to arise from violent mergers of compact objects, such as neutron star pairs or a neutron star colliding with a black hole. These mergers have recently been linked to the production of heavy elements, like gold and platinum, through a process called rapid neutron capture, or R-process nucleosynthesis. One of the hallmark detections fueling GRB studies was GRB 170,817A, observed in 2017, which coincided with gravitational waves from a neutron star merger. This event provided a multi-messenger view, capturing both gravitational and electromagnetic signals from the same cosmic cataclysm, and confirming key theories about the origins and mechanics of short-duration GRBs. While these gamma-ray bursts last for mere seconds or minutes, their afterglows, lower energy emissions in X-ray, ultraviolet, optical, and radio wavelengths, can be detected for days or weeks, allowing astronomers to pinpoint their locations billions of light-years away. These detections continue to expand our understanding of how the most massive stars end their lives, and how the universe creates and disperses some of its heaviest elements. In comparing these phenomena, it's striking how each represents a different scale and mechanism of cosmic explosion. Supernovae embody the explosive deaths of individual stars. Quasars harness the sustained energetic processes near supermassive black holes, and gamma-ray bursts pack ultra-powerful jets of energy from cataclysmic events into fleeting but intensely bright bursts. Collectively, they reveal a universe that is far from static, instead marked by violent, transformative episodes shaping the cosmic landscape over billions of years. But the story does not end with just cataloging these events. Understanding them enriches our knowledge of where everything comes from. Supernovae forge and spread the elements heavier than hydrogen and helium, the essential building blocks of planets and, ultimately, life itself. Quasars influence the conditions in the early universe, shaping the environments where galaxies grow and evolve. Gamma-ray bursts illuminate some of the most extreme physics known and spotlight the processes underlying the cosmic production of precious metals and other heavy materials. Through efforts combining telescopes sensitive to different wavelengths, space observatories, ground-based detectors, and even gravitational wave observatories, science continues to delve into these violent explosions. Each discovery reveals new clues about the origins, evolution, and destiny of the universe. In addition, studying these events helps us place our own solar system and planet in context, showing explicitly that Earth is a product of violent cosmic processes stretching back billions of years. With today's advanced tools, scientists can monitor supernovae from millions of light-years away, trace the evolution of quasars in distant galaxies, and detect gamma-ray bursts exploding in the far reaches of the visible universe. These observations not only tell us about the mechanics of cosmic explosions, but also push the boundaries of physics, testing theories of gravity, nuclear reactions, relativistic jets, and the nature of matter under extreme conditions. Looking ahead, missions like the James Webb Space Telescope promise to peer deeper into the universe's history. potentially witnessing these cosmic fireworks closer to their origins than ever before. Similarly, next-generation gravitational wave detectors and gamma-ray observatories will deepen our grasp of the violent mergers and explosions that fuel gamma-ray bursts. As researchers continue to study these powerful phenomena, we can expect profound insights into the ultimate forces shaping the cosmos, and, by extension, the universe that surrounds us. Each explosion, in all its staggering power, serves as a reminder that the universe is a dynamic place, full of events both destructive and creative. By unpacking the secrets of supernovae, quasars, and gamma-ray bursts, astronomers unravel the narrative of cosmic history from the remnants of massive stars to the energetic hearts of galaxies, to the briefest and brightest outbursts signaling the death throes of extreme stellar objects. These titanic explosions not only fuel the cycles of cosmic matter, but also illuminate the principles governing the fabric of reality itself. Exploring even more extraordinary explosions beyond supernovae, quasars, and gamma-ray bursts leads us to the realm of cosmic phenomena that, while less commonly discussed, are nonetheless pivotal in understanding the universe's most powerful energy releases. One such phenomenon involves magnetars, highly magnetized neutron stars whose magnetic fields are the strongest in the known universe. Though smaller and less luminous over time than quasars or gamma-ray bursts, magnetars create explosions in the form of intense bursts and flares, driven by magnetic reconnection or crustal shifts, unleashing vast amounts of energy in brief episodes. Magnetars exist as remnants of massive stars, packing roughly 1.5 times the mass of our Sun into a sphere only about 20 kilometers across. Their defining characteristic is the magnetic field strength, which can exceed 1011 Tesla, 1 trillion times stronger than Earth's magnetic field. This concentrated magnetic energy can twist and crack their solid crust, releasing sudden bursts of X-rays and gamma rays in events known as soft gamma repeaters, SGRs, or anomalous X-ray pulsars, AXBs. The most famous event linked to a magnetar occurred on December 27, 2004, when the magnetar SGR 18-6-20 erupted in a giant flare. This flare was so powerful that it briefly altered Earth's ionosphere, despite originating more than 50,000 light-years away. Though these magnetar flares release less energy than a typical gamma-ray burst, they demonstrate extreme magnetic processes capable of powering intense, rapid explosions, helping broaden our understanding of how magnetic fields influence compact, object behavior, and high-energy astrophysics in general. Their sudden bursts contrast with the longer, sustained release mechanisms in quasars, or the cataclysmic collapse and mergers producing supernovae and GRBs, highlighting the range of explosive phenomena in the universe. Another fascinating cosmic explosion to consider is the collision of black holes, a class of events primarily detected through the observation of gravitational waves rather than traditional electromagnetic signatures like light or X-rays. When two black holes spiral inward and merge, they release a tremendous amount of energy in the form of ripples in spacetime itself. These gravitational waves carry away a fraction of the combined mass energy of the black holes, sometimes equivalent to several solar masses converted directly into gravitational radiation over a span of milliseconds. The first direct detection of gravitational waves in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory. Collaboration confirmed predictions from Einstein's general theory of relativity made a century earlier. The detected signal, known as G150,914, revealed merging black holes around 30 solar masses each, releasing energy on the order of 5 × 10^47 joules. This energy release is enormous, surpassing the total electromagnetic luminosity of all the stars in a galaxy combined during the brief instant of merging. But because gravitational waves are so weakly interacting, They pass through matter with virtually no obstruction, making them invisible except to exquisitely sensitive detectors. Unlike electromagnetic explosions, like those seen in supernovae or gamma ray bursts, merging black holes provide a new means of hearing cosmic explosions. This revolutionizes our ability to study the violent processes happening in the darkest, most extreme corners of the universe, where no light escapes. Since 2015, dozens of black hole mergers have been observed, steadily characterizing the population of these enigmatic objects and their roles in galaxy evolution. While black hole mergers involve enormous energy release, another class of coalescing cosmic bodies, neutron star mergers, emphasizes a more visible form of cosmic explosion. When two neutron stars collide, they create powerful outbursts known as kilonovae, which are brief but extraordinarily luminous events, emitting across a wide range of wavelengths. These mergers not only generate gravitational waves, but also forge some of the heaviest elements in the universe through rapid neutron capture, or our process, nucleosynthesis. Elements like gold, platinum, and uranium are thought to be primarily produced in these explosive events. The landmark detection in 2017 of the neutron star merger G170,817 showcased this dual nature spectacularly. It delivered gravitational waves directly followed by a short gamma ray burst and an optical kilonova. This event provided some of the most compelling evidence, yet that neutron star mergers seed the cosmos with precious heavy elements and serve as crucial contributors to the chemical enrichment of galaxies. The electromagnetic signatures from these kilonovae evolve rapidly, from intense brightness days after the merger to gradually fading over weeks, giving scientists a unique window into the physics of dense matter and nuclear processes at extreme conditions. Aside from these astrophysical feats, the early universe itself may have experienced enormous energy releases during its infancy, beyond standard stellar or black hole activity. Moments after the Big Bang, during the epoch known as cosmic inflation, the universe expanded exponentially at speeds exceeding that of light, driven by a highly energetic quantum field. Though this was not an explosion in the traditional sense, the rapid release of energy stored in this field shaped the large-scale structure of the universe as we observe it today. The eventual reheating phase following inflation converted vacuum energy into the hot particle soup that led to the formation of matter and radiation, representing the first transition of energy from a concentrated state into the expanding space. Exploring relic signatures from the inflationary period, such as patterns in the cosmic microwave background radiation or primordial gravitational waves, remains a key frontier in cosmology. These hidden signals carry clues about the earliest cosmic explosions, in a broad sense, helping to anchor our understanding of how the universe grew from an almost featureless beginning into the richly structured cosmos, imprinted with galaxies, stars, and planets. On a smaller scale, but no less impactful in the grand cosmic narrative, energetic outflows from active galactic nuclei, AGN, complement the influence of quasars. AGN are powered by the accretion of matter onto supermassive black holes, but come in many flavors, including radio galaxies and Seyfert galaxies. They produce powerful jets of highly energetic particles extending across hundreds of thousands of light years. These jets, often seen in radio wavelengths, inflate enormous lobes of plasma outside the host galaxy, affecting the intergalactic medium by heating gas and suppressing star formation far beyond the galaxy's boundaries. These AGN jets serve as giant cosmic blowtorches, moving energy and matter across vast distances and helping regulate galaxy evolution over billions of years. In some cases, these jets punch through galactic gas, triggering new waves of star formation in compressed clouds, while in others they clear out gas reservoirs, halting future stellar birth. This dual role showcases how explosions and energy releases at galactic centers influence not only their immediate surroundings, but also the broader cosmic environment. Further, the impact of massive star-forming regions can generate enormous explosions known as superbubbles or superwinds. When large clusters of massive stars evolve and simultaneously undergo supernova explosions, their combined energy output drives outflows of hot gas into interstellar and intergalactic space. These phenomena distribute heavy elements and help transport energy beyond the galactic disk. Observations of galaxies with active starburst regions reveal these superwinds reaching speeds of hundreds to thousands of kilometers per second, influencing galaxy evolution and contributing to the enrichment of the intergalactic medium. Such starburst-driven explosions provide a complementary aspect of cosmic energy release beyond individual supernovae or black holes. They highlight how collective processes in stellar nurseries can reshape galactic ecosystems, illustrating interconnectedness between star formation, stellar death, and galactic-scale feedback mechanisms. In our own galaxy, the Milky Way, evidence for past explosions exists in the form of mysterious structures seen in gamma rays, known as the Fermi bubbles. These massive lobes extend roughly 25,000 light-years above and below the galactic plane and are believed to be remnants of enormous energetic events in the center of our galaxy. The leading hypotheses suggest that either past AGN activity, when the Milky Way's central black hole underwent an active feeding phase, or a series of intense starburst episodes triggered these explosive outflows. The Fermi bubbles demonstrate how a galaxy can retain scars of explosive energy releases over millions of years, providing a fossil record of dynamic processes at its core. Ongoing observations seek to understand the nature, timing, and causes of these structures, expanding our understanding of how galaxies cycle energy between their centers and outer regions. Shifting our gaze to extragalactic scales, galaxy clusters, the largest gravitationally bound objects in the universe, also exhibit evidence for powerful explosive events. The hot, X-ray emitting gas that fills clusters often shows cavities or bubbles carved out by relativistic jets from central supermassive black holes. These AGN feedback bubbles influence cluster gas by preventing catastrophic cooling and star formation, offering a key piece in explaining how galaxy clusters evolve. These cavities can be tens of thousands of light-years across and represent the mechanical energy output of black holes sustained over millions of years. The energy injected by these explosions helps maintain the delicate balance between heating and cooling in the intracluster medium, preserving the structural integrity of galaxy clusters and influencing the growth of their member galaxies. Considering all these phenomena together presents a rich spectrum of powerful explosions ranging from the death throes of individual stars to sustained energetic processes surrounding supermassive black holes, to colliding compact objects warping spacetime. While their mechanisms differ, each plays an essential role in shaping the universe's evolution and the creation of its chemical and structural diversity. Although the Big Bang itself was the primal explosion setting the stage for everything that followed, it is these subsequent titanic events, occasional yet immensely powerful, that continue to sculpt the universe in dramatic ways. By investigating these explosions across different scales and time periods, scientists unlock a detailed blueprint of cosmic history, shedding light on fundamental astrophysical processes and sometimes even revealing surprising connections among seemingly disparate phenomena. Understanding these explosive events also has a profound impact on various fields of physics, from nuclear and particle physics to gravitation and quantum mechanics. For example, neutron star mergers test the limits of matter under immense density, helping to refine equations of state for nuclear matter. Studying relativistic jets from black holes challenges models of magnetohydrodynamics and high-energy particle acceleration. Gravitational wave detections probe the very nature of spacetime, offering opportunities to test general relativity in the strongest fields. Moreover, Explosions such as supernovae enrich the cosmos with life-essential elements, and their remnants seed the formation of new stars and planetary systems, creating cycles of cosmic renewal fundamental to our very existence. Black hole activity regulates galaxies, helping determine their size and star-forming potential, while gamma-ray bursts highlight the most extreme conditions under which matter can exist. As telescopes and observatories continue to advance, revealing explosions in unprecedented detail, from the radio, infrared, optical, ultraviolet, X-ray, and gamma-ray bands to gravitational wave signals, our understanding will deepen, and our models of the universe will become increasingly comprehensive. Each new observation uncovers nuances about the origins, evolution, and interconnections of these powerful events. Ultimately, cosmic explosions, whether brief flashes or prolonged outbursts, represent the universe's most dynamic forces, driving change on scales vast and fundamental. They illuminate the mechanisms that govern the cosmos, the transitions from one state of matter or energy to another, and the relentless interplay between creation and destruction that defines the cosmos as a whole. Beyond these grand phenomena lies another category of spectacular cosmic explosions, those associated with the mysterious realm of primordial black holes and hypothetical phase transitions in the early universe. While these events remain more speculative in nature, rooted in theoretical physics and cosmology, they offer intriguing possibilities that could further expand our understanding of powerful energy releases in the cosmos. Primordial black holes, if they exist, are thought to have formed shortly after the Big Bang, arising from density fluctuations in the extremely hot and dense early universe. Unlike black holes formed by collapsing stars, primordial black holes could span a wide range of masses, from as small as an asteroid to many times the mass of the Sun. One remarkable prediction about the smallest primordial black holes involves a phenomenon called Hawking radiation. Proposed by physicist Stephen Hawking in the 1970s, this radiation suggests that black holes slowly evaporate by emitting particles due to quantum effects near their event horizons. As smaller primordial black holes shrink, this evaporation accelerates, culminating in a final explosive burst of energy, releasing intense radiation in a fraction of a second. Though such explosions have yet to be observed, their detection would open a new window on quantum gravity and early universe conditions. Another early universe explosive candidate comes from cosmic phase transitions, dramatic changes in the fundamental fields that govern the universe's initial state. As the universe cooled and expanded from its primordial high-energy state, it likely underwent transitions akin to water freezing into ice, but involving the fundamental forces and particles. Some theories predict that these phase transitions could have been first-order, proceeding via bubble nucleation. Regions of the new lower energy phase forming and rapidly expanding, colliding with one another and releasing enormous amounts of energy in the process. These transitions may have produced bursts of gravitational waves distinct from those generated by astrophysical mergers, potentially detectable by future observatories. Detecting such primordial gravitational waves would provide a direct probe of physics at energy scales unreachable by any terrestrial experiments, offering insights into the unification of forces and the very origins of our universe. Current searches leverage detectors like LIGO and Virgo, alongside proposed space-based observatories such as LISA and Pulsar timing arrays, to seek these subtle cosmic signatures. Moving back to more established phenomena, another form of powerful cosmic explosion arises during the tidal disruption events, TDEs. These occur when an unfortunate star ventures too close to a supermassive black hole lurking at a galaxy's core. The immense gravitational gradient stretches and pulls the star apart, a process aptly described as spaghettification. As stellar material spirals inward, it heats dramatically and emits intense bursts of X-ray, ultraviolet, and sometimes optical radiation. These explosive flares can outshine the entire galaxy temporarily, signaling the black hole's ravenous meal. TDEs provide unique laboratories to study accretion physics under extreme conditions. Observations of these rare events have become more frequent with advances in all-sky transient surveys, helping astronomers understand how supermassive black holes grow and interact with their environments. The timescales of TDE flares span weeks to months, but the initial explosive heating of stellar debris funnels enormous power in relatively brief periods. Interestingly, the aftermath of some TDEs can even launch relativistic jets, resembling scaled-down versions of AGN jets, which further amplify their explosive impact. These jets produce high-energy emissions across the electromagnetic spectrum and, in some cases, have been associated with powerful radio afterglows. Studying these events informs models of jet formation and the role of magnetic fields threading the black hole and incoming debris. Zooming out to cosmic structures, galaxy mergers themselves can trigger vast explosions of star formation known as starburst episodes. When galaxies collide, vast clouds of cold gas compress, triggering intense waves of stellar births. This rapid conversion of gas into stars results in powerful winds powered by the combined effects of massive stars and supernova explosions. These galaxy-wide outflows drive shocks that can expel gas into intergalactic space at hundreds or thousands of kilometers per second. The mechanical energy released in these superwinds not only regulates further star formation within merging galaxies, but also enriches the surrounding medium with heavier elements. In particular, cases like the Antennae galaxies or the nearby starburst Galaxy Mate-2 showcase how galaxy collisions can foster energetic episodes with properties resembling scaled-up superbubbles. These processes play a pivotal role in the evolution of galaxies by redistributing gas, affecting future star formation capacities, and shaping their morphological transformations over time. Complementing starbursts are the enigmatic ultraluminous X-ray sources, ULXs, some of which are powered by stellar mass black holes or neutron stars accreting mass at extraordinary rates. These objects often produce intense X-ray emissions, exceeding what is expected from typical stellar remnants. It is now understood that many ULXs are associated with highly super-Eddington accretion, the phenomenon where matter falls onto the compact object at rates surpassing the theoretical Eddington limit, leading to powerful outflows and radiation-driven winds. Such systems represent explosive accretion episodes on smaller scales, illustrating how compact objects can convert gravitational energy into luminous and kinetic energy vigorously. Studying ULXs helps bridge the gap between stellar and supermassive black holes, providing clues to the dynamics of matter under extreme gravity and radiation pressure. Another lesser-known but extremely energetic class of explosions arises from the collapse of very massive stars, particularly those above roughly 260 solar masses, which are predicted by stellar evolution models to end in parent-stability supernovae. These supernovae occur when the star's core reaches such high temperatures that energetic gamma photons convert into electron-positron pairs. This conversion removes pressure support and triggers a runaway contraction followed by explosive oxygen and silicon burning. The result is a titanic blast that completely disrupts the star, leaving no remnant black hole or neutron star behind. The energy released in a parent-stability supernova can be several times greater than a typical core collapse supernova, up to 1053 ergs, 1046 joules, and the brightness can outshine entire galaxies temporarily. These explosions are thought to have been more common in the early universe when massive, metal-poor population III stars formed. Studying their remnants and searching for candidate events helps astronomers understand the properties of the first stars and the seeding of heavy elements necessary for later generations of stars and planets. Parent-stability supernovae stand apart due to their unique mechanism and potential to influence early cosmic chemical evolution, demonstrating the diverse ways in which stars end their lives in explosive fashion. In a similar vein of extreme stellar events, hypernova deserve special mention. Hypernova represent a subtype of core-collapse supernovae associated with particularly massive stars that collapse to form black holes while producing exceptionally energetic explosions. They often coincide with long-duration gamma-ray bursts and are characterized by explosion energies 10 or more times greater than typical supernovae. These extraordinary explosions result in powerful jets plowing through the star, releasing enormous kinetic and radiation energy that can be observed across multiple wavelengths. Hypernova play a crucial role in delivering large amounts of heavy elements and metals into the surroundings, influencing star formation and galaxy evolution on broader scales. On the galactic scale, massive star clusters themselves can be sources of explosive feedback. Young, dense clusters containing numerous massive stars produce powerful stellar winds and supernova explosions in relatively compact volumes of space. The combined energy from these events creates expanding bubbles of hot gas, often bordered by shock fronts visible in X-rays and optical emission lines. Over millions of years, these superbubbles can grow to sizes of hundreds of light years and drive galactic-scale outflows if they break through the galactic disk. These feedback mechanisms regulate star formation locally and contribute to cycling material and metals between the interstellar and intergalactic medium. The study of such collective stellar explosions illuminates how interactions between stars, not just individual deaths, shape their environments, emphasizing the interconnectedness of cosmic ecosystems. Returning to the topic of energetic outflows, one cannot overlook the cosmic rays, high-energy particles zooming through space near the speed of light. While cosmic rays themselves aren't explosions in the classical sense, they represent energetic debris from past cosmic blasts, primarily supernova remnants. Supernova shock waves accelerate protons and nuclei to ultra-relativistic velocities, distributing these particles throughout the galaxy and beyond. These cosmic rays impact planetary atmospheres, influence star formation, and contribute to chemical reactions in interstellar space. Tracking their origin and propagation provides indirect insight into the history and magnitude of explosive events that produced them. Furthermore, cosmic rays serve as probes of magnetic fields, turbulence, and the physical conditions within explosive remnants, extending the legacy of cosmic explosions into ongoing, pervasive effects. Intriguingly, on the scale of entire galaxy clusters, the interplay between supermassive black hole activity and the intracluster medium produces vast cavities and shock fronts visible in X-rays. The energy injected over millions of years by jets from central black holes inflates enormous bubbles of relativistic plasma, up to hundreds of thousands of light years in size, displacing cluster gas and creating ripples akin to sonic booms. These cluster-scale explosions help prevent the hot gas from cooling and forming stars excessively, regulating the growth of the most massive galaxies. Observations of these phenomena, through high-resolution imaging from telescopes like Chandra and XMM Newton, have uncovered complex feedback loops that demonstrate how explosive energy release governs structure formation on the largest observable scales. In an altogether different arena, explosive phenomena also emerge from our own solar system, illustrating that power and transformation aren't reserved just for distant, cosmic scales. Solar flares and coronal mass ejections are energetic outbursts on the sun's surface caused by magnetic reconnection in the solar corona. These events release enormous amounts of energy, up to 10-25 joules in a single flare, briefly accelerating particles and emitting radiation across the electromagnetic spectrum. Though tiny compared to cosmic explosions in black holes or supernovae, solar flares affect space weather near Earth, influencing satellites, power grids, and communication systems. These local explosions provide a laboratory accessible to direct observation for studying magnetic energy release and plasma physics processes. By understanding solar flares, we gain insights applicable across scales, from stellar magnetars to extragalactic jets. Another point worth considering is the scale of explosive energy in relation to their potential for impact. For instance, while gamma-ray bursts and black hole mergers release incomprehensibly huge amounts of energy in very short bursts, their effects on Earth and life depend greatly on distance and orientation. A gamma-ray burst aimed directly at Earth from within a few thousand light-years could pose significant threats by damaging the atmosphere's protective ozone layer. But such events are exceedingly rare. Similarly, the explosion of a nearby supernova would shower Earth with radiation and cosmic rays, possibly influencing biological evolution by triggering extinctions or mutations. But again, the probabilistic frequency and proximity condition their impact. This interplay of global energy output and localized relevance highlights how astronomical explosions shape not only cosmic history, but potentially the destiny of life on our own planet, weaving together the threads of astrophysics, biology, and geology. Looking ahead, new technologies promise to uncover even more explosive secrets. Next-generation observatories, both on Earth and in space, such as the James Webb Space Telescope, upcoming gravitational wave detectors, like the Einstein Telescope and Cosmic Explorer, and sensitive neutrino and gamma-ray instruments are set to probe the transient universe with unprecedented precision. These advances will enable detection of fainter, more distant, or shorter-lived explosive phenomena, help clarify ambiguous event classifications, and test fundamental physical laws under extreme conditions. For example, anticipated observations of neutron star mergers across cosmic times will constrain how elements formed throughout cosmic history, while better gravitational wave sensitivity may reveal black hole interactions not yet imagined. In addition, multi-messenger astronomy, the combined study of electromagnetic signals, gravitational waves, neutrinos, and cosmic rays, continues to revolutionize our understanding by correlating signals from the same explosion across different carriers of information. This approach enriches our view of explosive processes, unveiling the full complexity of energy release, matter behavior, and particle acceleration. In sum, while the Big Bang stands as the ultimate primordial explosion, the universe remains a dynamic stage for a dazzling array of powerful energy releases. From stellar deaths and compact object mergers to galactic outflows and the early universe's phase transitions, these explosions drive the cosmic cycle of matter and energy, shaping the universe's large-scale structure, chemical diversity, and even the potential for life. Each explosive event, whether a sudden blip detected in gamma rays or a gradual expansion of hot gas over millions of years, adds depth and texture to the grand narrative of how the cosmos evolves and transforms. The ongoing exploration of these phenomena not only satisfies human curiosity about the cosmos, but also informs fundamental physics and the conditions enabling the existence of everything we know. Among the most remarkable discoveries in recent decades has been the ability to detect gravitational waves, ripples in the fabric of spacetime produced by some of the universe's most energetic and cataclysmic events. The groundbreaking detections by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have opened a new and exciting window onto explosive phenomena, revealing cosmic collisions and mergers that were previously hidden from view. Gravitational waves are generated when massive, dense objects accelerate asymmetrically. The first confirmed detection, announced in 2016, came from the merger of two stellar mass black holes about 1.3 billion light-years away. This collision released an energy burst equivalent to several solar masses, converted directly into gravitational wave energy in less than a second. making it one of the most powerful explosions ever recorded in the universe since the Big Bang. Unlike electromagnetic radiation, light, gravitational waves pass through matter almost unhindered, carrying pristine information about the events that created them. These detections have since broadened our conception of explosive events. Beyond black hole mergers, scientists have observed signals from neutron star mergers, events where two ultra-dense remnants of massive stars spiral inward and collide. These neutron star collisions produce gravitational waves alongside bright explosions known as kilonovae. Powered by heavy element synthesis through rapid neutron capture, the ARP process, the observation of gravitational waves from a neutron star merger in 2017, coincident with gamma rays and optical emissions, confirmed long-standing theories about the origins of gold, platinum, and other heavy elements that enrich the cosmos. The capacity to measure and interpret gravitational waves has expanded the cosmic catalog of explosions, capturing events that occur quietly in space, void of bright electromagnetic signals, yet tremendously powerful in gravitational energy release. The insights derived from these observations also test the fundamental nature of gravity and spacetime under extreme conditions, placing constraints on competing models of black hole physics and neutron star interiors. Beyond individual stellar remnants, supermassive black holes at galactic centers can also produce gravitational waves when they merge, a phenomenon anticipated to generate some of the most intense gravitational explosions, releasing energy trillions of times greater than their smaller counterparts. Detecting these events will require next-generation space-based observatories like LISA, Laser Interferometer Space Antenna, expected to launch in the 2030s. Such missions will enable the study of black hole mergers across cosmic history, illuminating how galaxies and their central black holes grow in tandem through hierarchical cosmic assembly, while gravitational waves spotlight the explosive death throes of dense objects. Another set of powerful detonations is intimately linked to the life cycles of massive stars in the universe. Though standard supernovae have been discussed extensively, there exist rarer, even more energetic variants that defy classical classification. One such phenomenon is the magnetar giant flare, a sudden burst of high-energy radiation and particles from a magnetar, a neutron star possessing magnetic fields trillions of times stronger than Earth's. These flares can briefly outshine entire galaxies in high-energy wavelengths, such as gamma rays and X-rays. Magnetars are believed to form from the collapse of especially massive stars or through magnetic field amplification processes in neutron stars. Occasionally, an unstable rearrangement of their magnetic field induces a catastrophic release of energy. A famous example occurred in 2004 when a giant flare from a magnetar in our own galaxy produced a burst so intense it affected Earth's ionosphere despite being 50,000 light-years away. While not as energetic overall as supernova explosions, magnetar flares occur on a much shorter timescale, milliseconds to seconds, and represent violent disruptions of neutron star magnetospheres. The study of magnetar flares also intersects with that of fast radio bursts, FRBs, brief but intense pulses of radio waves detected from distant galaxies whose origins are still not fully understood. Some theories propose magnetar activity as a potential source, meaning that these brief cosmic flashes might be linked to explosive magnetic events. Expanding on the theme of magnetically driven explosions, solar system phenomena provide more local examples of how magnetic energy accumulation and sudden release can produce powerful outbursts. Beyond solar flares, coronal mass ejections, CMEs, expel billions of tons of plasma from the sun's outer atmosphere at millions of kilometers per hour. When directed toward Earth, CMEs interact with our planet's magnetic field, causing geomagnetic storms that can damage satellites, disrupt power grids, and produce spectacular auroras. The energy released in a CME is substantial, comparable to millions of nuclear bombs detonating simultaneously, highlighting that explosive magnetic energy release is not confined to distant astrophysical objects, but is an everyday solar phenomenon with direct terrestrial impact. Switching focus to yet larger scales, the role of explosive events in shaping the intergalactic medium, the tenuous gas filling the space between galaxies, cannot be overstated. Feedback from active galactic nuclei, AGN, powered by accretion onto supermassive black holes, can launch wide-reaching outflows that carry enormous energy and momentum far beyond their host galaxies. These outflows can quench star formation by expelling or heating galactic gas, thereby regulating galactic growth in a process called AGN feedback. Among the spectacular expressions of AGN feedback are radioloud quasars and radio galaxies, whose jets and lobes inflate cavities within the hot gas of galaxy clusters, visible as vast, bubble-shaped voids in X-ray images. The energy input into the intracluster medium from these bubbles can reach 1060 ergs or more, equivalent to the energy output of millions of supernovae combined over millions of years. This continuous, large-scale energy injection prevents catastrophic cooling of cluster gas, maintaining a delicate balance that shapes galaxy formation on scales of millions of light years. Moreover, shocks driven by AGN jets and cluster mergers accelerate particles to relativistic speeds, producing cosmic rays and non-thermal radiation detectable across radio to gamma ray bands. This complex interplay illustrates that explosive processes are not isolated moments, but can seed long-lasting energetic phenomena influencing environments across cosmic timescales. Further into the realm of cosmic gigantism, some of the most enormous explosions come from gamma-ray bursts, GRBs, the brightest and most energetic explosions known in the universe, outside of the Big Bang itself. GRBs are brief flashes of gamma radiation that can last from milliseconds to several minutes, detected from billions of light years away. Their energy output during these bursts can equal the total energy our sun will emit over its entire 10 billion-year lifetime, concentrated into highly collimated jets moving near the speed of light. GRBs typically fall into two categories: short-duration bursts lasting less than 2 seconds, linked to mergers of compact objects like neutron stars, and long-duration bursts associated with the collapse of massive stars in hypernova-like explosions. Their detection revolutionized high-energy astrophysics and deepened our understanding of relativistic jets, black hole formation, and nucleosynthesis. The collimated nature of GRB jets means that much of their energy is beamed in narrow cones, making them observable only when the jet points toward Earth. This jetting also implies that the true energy of the explosion can be even greater, though spread unevenly. Observations across wavelengths, gamma rays, X-rays, optical, and radio, trace the evolution of the afterglow produced as the jets interact with the surrounding medium, providing a detailed look at explosion physics and environments. In some rare cases, GRBs are also thought to produce extremely energetic neutrinos, near massless, neutral particles that can travel unhindered across the universe, offering another channel to study these explosive events. Though direct detection of neutrinos from GRBs remains elusive, improvements in neutrino observatories portend imminent discoveries. Another compelling front in the study of cosmic explosions involves the interplay between stellar explosions and the formation of compact star clusters and even entire dwarf galaxies. Massive star clusters can experience collective supernova explosions in rapid succession, a phenomenon known as a supernova cluster wind that carves out enormous cavities in surrounding gas and drives galactic-scale outflows. These outflows can trigger secondary star formation in compressed shells or hem the escape of metals and energy into the intergalactic medium. In dwarf galaxies, where star formation episodes may be brief but intense, Such explosive feedback plays an outsized role in determining their evolutionary paths. Observationally, regions such as the Tarantula Nebula in the Large Magellanic Cloud offer nearby laboratories to study clustered massive star formation and the resulting cumulative explosion effects. Superbubbles, hundreds of light years wide cavities filled with hot gas created by overlapping stellar winds and supernovae, serve as evidence of these combined explosive processes and provide key insights into the cycling of matter. On a more fundamental level, understanding these multi-scale explosions reveals how energies produced by individual stars can influence galactic dynamics, demonstrating that the cosmos is a patchwork of nested explosive phenomena, each contributing to the larger cosmic story. Turning back to more speculative but scientifically grounded frontiers, the potential role of exotic particles and fields during the universe's infancy remains an area of active investigation. Some models in particle physics suggest that processes such as axion field misalignments or decay of topological defects, like cosmic strings or domain walls, could have injected bursts of energy analogous to explosions, though on scales and with signatures differing from classical astrophysical events. While experimental verification remains pending, studies of the cosmic microwave background, large-scale structure, and gravitational wave background seek signatures consistent with such occurrences. If detected, these could represent hitherto unobserved classes of explosive phenomena, blending particle physics and cosmology in a profound way. Altogether, the spectrum of powerful explosions since the Big Bang extends from the most energetic gravitational wave bursts signaling black hole mergers to the magnetic outbursts of neutron stars. From grand-scale quasar, jet-sculpting galaxy clusters to local solar flares influencing our technological civilization, each category of explosion plays a distinctive role, driving chemical enrichment, shaping star and galaxy formation, testing the laws of physics in extreme conditions, and, perhaps most remarkably, connecting the life and death of stars to the evolution of the entire universe. Exploring these phenomena continues to be at the forefront of astrophysics, propelling advances in observational technology, theoretical modeling, and cross-disciplinary inquiry. By unearthing the secrets of these cosmic blasts, scientists not only deepen our understanding of the universe's past, but also prepare to answer what may be some of the most profound questions of all. How did the universe evolve from the primordial fireball to the complex web of galaxies, stars, and planets capable of harboring life? And what grand cosmic fireworks will the universe produce next? Moving beyond explosive events tied to stars and black holes, a fascinating category of powerful detonations lies in the realm of cluster mergers. The colossal collisions between galaxy clusters, the largest gravitationally bound structures in the universe. Galaxy clusters contain hundreds or thousands of galaxies embedded within an enormous halo of dark matter, interspersed with a diffuse, extremely hot plasma known as the intracluster medium, ICM. When two such clusters collide, the energies involved are staggering, reaching scales many orders of magnitude beyond individual supernovae or even quasars. These cluster mergers unfold over hundreds of millions of years, during which the kinetic energy of the merging clusters, amounting to up to 1063 ergs, transforms into heat and shock waves within the ICM. The shocks can accelerate particles to near-light speeds, generating diffuse emission in radio and X-ray wavelengths detectable by observatories such as Chandra and XMM Newton. These shocks effectively constitute some of the universe's largest explosions since the Big Bang, distributing colossal amounts of energy throughout the clusters and influencing their evolution. One illustrative example is the famous Bullet cluster, located about 3.7 billion light-years away. The Bullet cluster is actually two galaxy clusters in the process of colliding at speeds of thousands of kilometers per second. Observations across multiple wavelengths have revealed a remarkable separation between the ordinary matter, predominantly hot gas, and the dark matter components. The interaction between the visible gas clouds produces a shock front that moves supersonically, hence the name bullet, leading to bright X-ray emission and turbulence within the cluster environment. Beyond its energetic significance, the bullet cluster provided crucial empirical evidence for the existence of dark matter. Since gravitational lensing measurements indicated mass distributions offset from the hot gas that dominates the ordinary matter. The immense power released during cluster mergers not only heats and stirs the gas, but also influences galaxy evolution within clusters. The ram pressure exerted on galaxies as they move through this turbulent medium can strip gas from them, quenching their ability to form new stars, a process known as ram pressure stripping. Thus, cluster mergers play a dual role. They generate some of the universe's most energetic shocks and help regulate galaxy life cycles on a grand scale. Astrophysicists also study the interplay between cluster mergers and active galactic nuclei to understand how these explosive processes collectively impact cosmic structure. For example, AGN jets in cluster centers often form cavities or bubbles in the intracluster gas, which may interact with merger-driven shocks to redistribute energy and influence thermal balance. This multi-component feedback loop underscores that explosive events occur in interconnected cosmic ecosystems across vast scales. On a related front, the concept of cosmic explosions extends into the early universe through phenomena like primordial black holes. These hypothetical objects, thought to have formed soon after the Big Bang under certain conditions, could have undergone evaporations via Hawking radiation. While direct evidence of primordial black holes remains elusive, their potential evaporation represents a different type of cosmic explosion, one born from quantum effects near event horizons, rather than classical astrophysical processes. If detected, such evaporations would provide unprecedented insights into the interplay between quantum mechanics and gravity. Meanwhile, recent advances in time-domain astronomy, the monitoring of the sky for transient events, have uncovered a host of unusual explosive phenomena that challenge traditional classifications. Among these are superluminous supernovae, SLSNI, which shine up to 100 times brighter than typical supernovae, and fast blue optical transients, FBOTS, which brighten and fade in days, much faster than expected. The physical mechanisms driving such events include extreme energy input from central engines like magnetars or interaction of ejecta with dense circumstellar material. But detailed understanding is still evolving. An example of a superluminous supernova is SN 2006 Gi, which radiated enormous amounts of energy, about 1051 ergs, in visible light alone. The enormous brightness points to an explosion involving massive star progenitors with extensive mass loss prior to collapse, possibly augmented by energy injection from a rapidly spinning neutron star or magnetar formed in the explosion. These discoveries expand the census of stellar explosions and offer new clues about how massive stars end their lives under rare conditions. Furthermore, the search for counterparts to gravitational wave detections has opened additional avenues for studying explosive phenomena. Events like kilinovae, briefly mentioned earlier, continue to provide crucial insights into how mergers of neutron stars synthesize heavy elements and shed material during their cataclysmic unions. These electromagnetic counterparts, observed across gamma-ray, optical, and infrared wavelengths, establish links between gravitational wave signals and classic, light-based astronomy, fostering a holistic picture of the explosive universe. Complementing these breakthroughs are observations of tidal disruption events, TDEs, where a star ventures too close to a supermassive black hole and is torn apart by immense gravitational forces. The sudden influx of stellar debris fuels a bright flare lasting months or years, sometimes accompanied by powerful jets emitting high-energy radiation. TDEs can momentarily outshine the entire galaxy's usual output, providing a natural laboratory for studying accretion physics and black hole feeding mechanisms. The combination of these various explosive processes, ranging from cluster mergers and exotic star deaths to tidal disruptions, demonstrates how the cosmos constantly reinvents its firepower beyond the spectacular fireworks of the early universe. Yet another angle to consider is the role of cosmic ray acceleration associated with these explosions. As shock waves propagate through gas in supernova remnants, galaxy clusters, or AGN jets, they energize charged particles to relativistic velocities. These cosmic rays contribute to the dynamics and chemistry of interstellar and intergalactic space, influencing star formation and magnetic field evolution. In summary, the catalog of the universe's most powerful explosions continues to grow more diverse and intricate. From the immense, slow-moving shocks of galaxy cluster collisions to the bright, brief flares of magnetars and tidal disruption events, these phenomena shape the universe on scales encompassing everything from the smallest particles to the largest cosmic structures. Studying them enriches our understanding of fundamental physics, the life cycle of matter, and the grand cosmic tapestry woven since the moment of the Big Bang. Such investigations promise to unravel deeper mysteries about the past, present, and future explosive forces that govern and transform the universe. Another exceptionally powerful category of explosions lies in the realm of gamma-ray bursts, GRBs. These brief but extraordinarily energetic flashes of gamma radiation represent some of the brightest electromagnetic events in the universe. Discovered in the late 1960s by military satellites designed to detect nuclear tests, GRBs initially puzzled astronomers with their unpredictable, intense bursts of high-energy photons. Subsequent study revealed that they originate at cosmological distances, releasing in seconds as much energy as the Sun does over its entire 10 billion-year lifetime. Gamma-ray bursts are generally divided into two classes based on their duration: long-duration GRBs, lasting more than about 2 seconds, and short-duration GRBs, which are briefer, typically under 2 seconds. Long GRBs are now firmly linked to the catastrophic deaths of massive stars in distant galaxies. As these stars exhaust their nuclear fuel, their cores collapse into black holes or neutron stars, driving highly relativistic jets of material outward at speeds close to that of light. When one of these jets is aligned toward Earth, it appears as a brilliant gamma-ray flash lasting from seconds to minutes. The incredible energies involved in GRBs arise from the conversion of gravitational energy released during the stellar collapse into kinetic energy of the jet and the subsequent radiation of gamma rays. These events emit a narrow beam rather than exploding isotropically, which means their total energy is less than implied by the apparent brightness, but still astonishing, typically on the order of 1051 to 1054 ergs. Short GRBs, on the other hand, are associated with the mergers of compact objects, such as two neutron stars or a neutron star and a black hole. These violent unions produce intense bursts of gamma rays lasting less than 2 seconds, but are often followed by afterglows in X-ray, optical, and radio wavelengths that can persist for days. The short GRB progenitors have garnered significant attention since the groundbreaking detection of gravitational waves from a neutron star merger in 2017, coinciding with a short GRB and a kilonova. This multi-messenger event confirmed that such mergers are a primary source of short GRBs and also a key site of heavy element production through rapid neutron capture nucleosynthesis. The importance of gamma-ray bursts extends beyond their immediate spectacle. Because they shine brightly across vast cosmic distances, GRBs serve as probes of the early universe. Some of the most distant GRBs observed occurred when the universe was just a few 100 million years old, providing rare glimpses into the conditions of early star formation and the intergalactic medium. Observations in different wavelengths allow astronomers to study the host galaxies and environments where these massive explosions occur. Moreover, the physics of GRBs offers insights into fundamental theories of relativity and particle acceleration. The jets ejected during these bursts travel at ultra-relativistic speeds with Lorentz factors, the measure of relativistic beaming, reaching several hundred or more. The mechanisms powering these jets and generating the high-energy gamma rays involve tightly coupled processes of magnetic field amplification, shock acceleration of charged particles, and detailed radiative interactions. Despite significant progress, many details about jet formation and emission still challenge theoretical models and ongoing observations. Beyond gamma-ray bursts, one must also consider the influence of the most extreme magnetic phenomena known as magnetars. These are neutron stars with extraordinarily strong magnetic fields, trillions of times stronger than Earth's, which can undergo sudden and powerful starquakes in their crusts. These events release vast amounts of energy in short bursts of X-rays and soft gamma rays known as magnetar flares. The most powerful recorded magnetar flare took place in 2004 from the source SGR 18-6-20, located about 50,000 light-years from Earth, and briefly outshone the entire Milky Way in gamma rays. Though smaller in total energy compared to GRBs, magnetar flares are notable for their intensity and the extreme physics involved in their emission. Magnetars also provide laboratories for studying the behavior of matter under extreme density and magnetic fields. Their bursts illuminate how superdense neutron star crusts fracture and how strong magnetic fields decay over time, affecting the emission and evolution of these objects. Understanding magnetars sheds light on the life cycle of neutron stars and the diversity of outcomes following massive star death. Moving up in scale once again, the realm of quasars and active galactic nuclei challenges astronomers with explosive activity at the hearts of galaxies, powered by accretion onto supermassive black holes millions to billions of times the mass of the Sun. Quasars represent some of the brightest persistent sources in the universe. While their emissions are generally more prolonged and steady compared to cataclysmic explosions like GRBs, quasars can generate explosive episodes on shorter timescales. Fluctuations in accretion rates, instabilities in the surrounding gas, or interactions with neighboring bodies can trigger luminous outbursts across the electromagnetic spectrum. Occasionally, quasars display enormous eruptions associated with sudden infall of matter or tidal disruption of stars, injecting vast amounts of energy into their host galaxies and beyond. These energetic outputs drive powerful jets of charged particles and radiation, producing radio lobes thousands of light-years in scale that sculpt the intergalactic medium. Such quasar-driven outflows are considered significant in galaxy evolution, regulating star formation by sweeping away gas or heating it to inhibit cooling. Central to this understanding is the concept of feedback, a process in which black hole activity influences the larger galactic environment. A particularly dramatic event linked to this feedback is the occurrence of tidal disruption events, TDEs, briefly explored earlier. When a star wanders too close to a supermassive black hole, the gravitational forces tear it apart, causing a rapid accretion of stellar debris and a luminous flare of energy that can outshine the entire galaxy temporarily. Observations of TDEs have expanded with recent time-domain surveys, revealing diverse emission properties and enabling the study of black hole masses, spins, and the physics of accretion under extreme conditions. TDE flares can vary dramatically in brightness and duration, depending on factors like the star's mass, the black hole's properties, and the geometry of debris fallback. Some events produce relativistic jets, resulting in transient gamma-ray emissions analogous in some ways to smaller-scale versions of GRBs. The study of TDEs bridges astrophysics and general relativity, providing direct insight into how black holes consume matter and influence their surroundings. While cosmic explosions mostly involve electromagnetic radiation and energetic particles, another dimension of these events comes from the realm of gravitational waves, the ripples in spacetime predicted by Einstein's theory of general relativity and directly detected only in the past decade. The merging of compact objects like black holes and neutron stars sends powerful gravitational waves across the universe, carrying information about mass, spin, distance, and the properties of extreme gravity. These cataclysmic mergers have revolutionized astronomy by inaugurating the field of gravitational wave astrophysics. Unlike light, gravitational waves are unaffected by dust or gas, offering a unique glimpse into otherwise obscured processes. The combined observation of gravitational waves and electromagnetic counterparts, as in the neutron star merger event G170,817, exemplifies how multi-messenger astronomy enriches our understanding of cosmic explosions. The energy radiated in gravitational waves during such mergers can reach around 1054 ergs, an astounding fraction of the total mass energy involved. Although gravitational waves themselves do not explode in the classical sense, the events producing them often generate explosive electromagnetic phenomena as well. Future observations of these mergers are expected to uncover yet more extreme examples, including black hole collisions with masses and spins that challenge existing models. Beyond individual events, the cumulative energy released by explosive processes across cosmic history has profound effects on the evolution of the universe. Explosions inject energy into the interstellar and intergalactic medium, influencing gas heating, chemical enrichment, and the distribution of matter. They contribute to the cosmic web's structure by heating hydrogen gas and modifying star formation rates, helping to explain observed large-scale patterns of galaxies and clusters. The fallout from such enormous energy releases is also evident in cosmic rays, high-energy charged particles continuously detected on Earth. Many originate from supernova remnants and shock fronts in clusters that accelerate particles to near-light speed. But some cosmic rays likely come from more energetic sources, like gamma-ray bursts or active galactic nuclei jets. Understanding the sources and propagation of cosmic rays has implications for particle physics and space weather alike. The study of explosive cosmic events, from the smallest neutron star flares to the largest cluster mergers, continues to advance rapidly thanks to improving instruments and new observational techniques. Space-based telescopes sensitive to gamma rays, X-rays, and ultraviolet light, combined with ground-based optical, radio, and gravitational wave detectors, provide complementary perspectives. Surveys monitoring transient events in real time enable astronomers to capture the earliest stages of explosions, refining models and matching theory with observation. In addition, high-performance simulations provide theoretical laboratories for understanding the extreme physics driving these explosions. Complex interactions of gravity, magnetism, nuclear forces, and radiation are modeled with increasing sophistication, allowing researchers to predict signatures and guide observations. This synergy between observation, experiment, and computation enriches our comprehension of how matter behaves when pushed to its limits. In summary, powerful cosmic explosions manifest across a vast range of scales and mechanisms, each illuminating different aspects of our universe. Whether through the jet-driven brilliance of gamma-ray bursts, the magnetic outbursts of magnetars, or the grand-scale shocks of colliding galaxy clusters, these events demonstrate the universe's capacity for both creation and destruction. Since the Big Bang set the stage for these violent transformations, the ongoing study of immense explosions provides not just awe-inspiring phenomena, but fundamental insights into the nature of matter, energy, gravity, and cosmic evolution. While the most luminous explosions in the cosmos often grab headlines, it's crucial to recognize the cumulative power of cosmic events happening on grand scales. One remarkable example unfolds when vast clusters of galaxies collide with one another. These collisions are not brief explosions like supernovae or gamma-ray bursts, but instead involve titanic interactions distributing staggeringly large amounts of energy over hundreds of millions of years. Galaxy clusters are the largest gravitationally bound structures in the universe, each containing thousands of galaxies, enormous reservoirs of hot gas, and vast quantities of dark matter. When two such clusters merge, the kinetic energy involved can reach levels greater than 10^64 ergs, many orders of magnitude beyond any single stellar explosion. This energy is not released all at once, but transforms into intense shock waves propagating through the hot gas in the clusters, heating it to temperatures of tens of millions of degrees. Such collisions directly influence the physical state of the intracluster medium, producing spectacular X-ray emissions that astronomers observe with space-based telescopes. The shocks generated during these events also accelerate particles to near-light speeds, creating extended radio emission regions known as radio relics. These relics serve as cosmic beacons, indicating the presence of powerful ongoing processes beyond singular bursts of light. While less like a traditional explosion in the sense of sudden flash or burst, merging galaxy clusters represent nature's slow yet colossal release of energy, illustrating how cosmic explosions scale up from stellar to supergalactic levels. Beyond shaping the thermal environment of clusters, these colossal mergers modify the distribution of dark matter and galaxies within clusters, influencing the large-scale structure of the universe. Another exceptional explosive event connected to the large-scale universe is the formation of cosmic voids and filaments, the elements of the cosmic web. While not explosions per se, these large-scale structures emerge through nonlinear gravitational processes that involve immense flows and sometimes violent collapse of matter over billions of years, leading to energy redistribution on enormous scales. Voids, vast expanses of relatively empty space, grow as matter flows into filaments and clusters. The motions of matter streaming into these dense regions can produce shock fronts and heat gas to extreme temperatures, releasing energy over cosmic timescales reminiscent of low-level but large-volume explosions. Returning to more distinctly explosive phenomena, recent advances in multi-messenger astronomy, the combined observation of electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, have opened new windows on cosmic explosions that were previously hidden or poorly understood. For example, some of the most powerful explosions are thought to be associated with blazars, a subclass of active galactic nuclei where jets emitted by the supermassive black hole point almost directly at Earth. Blazar flares can increase their brightness dramatically over short timescales, sometimes by factors of tens or hundreds. These flares emit over the entire electromagnetic spectrum, from radio waves to very high-energy gamma rays, suggesting extreme particle acceleration mechanisms at work close to the black hole. Significantly, blazars are also linked to the production of high-energy neutrinos, elusive subatomic particles that rarely interact with matter. The detection of neutrinos coinciding with blazar flares provides direct evidence that these jets accelerate protons to extremely high energies, making them potential sources of some of the highest energy cosmic rays observed on Earth. These explosive processes present a unique intersection of astrophysics and particle physics, illustrating how the universe continuously pushes particles to energies far beyond human-made accelerators. Beyond such energetic events, the study of cosmic explosions also reveals the production of chemical elements essential for life and complexity. Classic supernovae and neutron star mergers are sites where heavy elements beyond iron are forged through rapid neutron capture processes. Gamma ray bursts and magnetar flares contribute to this enrichment, scattering these newly minted elements into surrounding space, where they eventually become part of new stars, planets, and ultimately biological organisms. This cosmic alchemy connects the most violent astrophysical events to the very conditions necessary for life's emergence. In the quest to understand these explosions, new telescopes and observatories continually expand our capabilities. Future missions will provide improved sensitivity and temporal resolution to capture more fleeting, distant, or faint explosions. Instruments operating at different wavelengths complement each other. For instance, new X-ray observatories will delve deeper into the details of magnetar bursts and accretion processes in black holes, while gravitational wave detectors, now entering their next phases, will observe mergers from farther reaches of the universe. These advances will refine our understanding of how often such powerful explosions occur and how they evolve over cosmic time. Attention is also turning toward the earliest energetic phenomena in the universe. The cosmic dawn, the era when the first stars and galaxies formed, likely witnessed a host of powerful explosions. These early supernovae and gamma ray bursts could have significant impact, shaping the reionization of the universe and initiating the metal enrichment of primordial gas clouds. Though currently beyond direct observation, indirect evidence from cosmic microwave background measurements and ongoing surveys of distant galaxies hint at a rich history of violent events deeply influencing the universe's early development. One important frontier in the study of cosmic explosions is the role of fast radio bursts, FRBs, a relatively recent discovery. These extremely brief yet intense bursts of radio waves last only milliseconds but emit enormous energy, comparable in a blink to the energy emitted by the sun over days or weeks. The origins of FRBs remain a vibrant area of research, with suggestions ranging from magnetar activity to exotic phenomena involving neutron stars or black holes. While not as energetically dominant as gamma ray bursts or supernovae, FRBs represent yet another form of explosive energy release, and their study is shedding light on the extreme physics at work in compact astrophysical objects. Taken together, the diverse range of explosions cataloged by astronomers, from the rapid collapse of massive stars, the collision of neutron stars, magnetar outbursts, and supermassive black hole flares to the slow, titanic merging of galaxy clusters, paints a comprehensive picture of the universe as a dynamic arena. In this arena, energy is continually transformed and reconfigured, driving evolution on scales from the atomic to the cosmological. Through intricate observational campaigns, theoretical models, and computational simulations, scientists continue to unravel the mechanisms behind these powerful explosions, enriching our understanding of fundamental physics, such as gravity under extreme conditions, nuclear reactions beyond the reach of terrestrial laboratories, and the behavior of matter under immense pressure and magnetic fields. The importance of these studies extends beyond academic pursuit. Learning how cosmic explosions distribute energy and matter helps illuminate the origins of the universe's structure, the conditions that gave rise to planets and life, and potentially the ultimate fate of the cosmos itself. Each explosion provides a data point on the grand timeline of cosmic evolution, reminding us that even the most violent phenomena contribute to creating the very universe we inhabit. As technology and methodology advance, the coming decades promise new discoveries and deeper insights into these awe-inspiring events. From detecting more distant gamma ray bursts to capturing the faintest gravitational waves from merging black holes far beyond our current reach, humanity's understanding of cosmic explosions will broaden further. In doing so, we step closer to comprehending the full scope of cosmic power, unleashed since the Big Bang and its enduring impact on the universe's past, present, and future.